So, welcome to this edition of GTV. We're very happy to have Jin telling us about knotted surfaces where he gets smaller numbers of RP2s. Our tradition is to just unmute and ask questions. If there's some reason why you can't talk, you can put something in the chat and somebody will try to monitor it and relay, but just shout things out. This said, I will turn off my video and mic and let Jin take it away. Thank you so very much.
Thank you for the invitation and thank you for introduction. My name is Jin Miyazawa. I am a student of the University of Tokyo. The title is a gauge theoretic invariant of embedded surfaces in four manifolds and exotic pizza knots. Let me explain the organization of this seminar. Firstly, in the first section, I will explain the main theorem and the background of the main theorem. And in the next section, I will explain real cybergate theory. This is a variant of cybergate theory. This is used to construct our invariant of embedded surfaces in four manifolds. And in the third section, I will explain other applications of our invariant. And if time permits, I will explain how to calculate our invariant for specific two knot. So let's start the seminar. So let X be a closed-oriented four manifold. So if two embeddings I and J of sigma to X are topologically or smoothly equivalent if and only if there exists homeomorphism or diffeomorphism such that they are topologically or smoothly isotopic to the identity and that satisfies this relation. We say that I and J are exotic if and only if they are topologically equivalent. However, they are not smoothly equivalent. So here is the main theorem. We have an infinite family of embedding of RP2 to S4 such that they are exotic. They are topologically isotopic. However, they are not smoothly equivalent. So let me explain the background of this theorem. There are great deal of studies of exotic surfaces in four manifolds. However, there are not so many studies of exotic surfaces in S4. For example, there's no known example of orientable exotic surfaces in S4. And to the best of my knowledge, these are the known example of unorientable surfaces in S4. The first example is given by Finashing, Clegg, below. This is given in 1987. They give an infinite family of exotic embedding of unorientable surface with genus 10. After that, there are several examples given. So recently, Matic, Oztak, and Stipchitz give an example of exotic unorientable surface with genus 5. So in these papers, to prove they are not smoothly equivalent, we have two steps. Firstly, we take the double-branched covers along the image of these embeddings. say X and X prime. They are double branched cover along these images. And in the next step, we prove X and X prime are not diffeomorphic. So if we try to detect exotic embedding of RP2 to S4 using this method, we have to find exotic CP2. So this is known to be difficult. So in this seminar, we construct an invariant of embedded surfaces using gauge theory, and we will detect exotic P2 knot. So here is the second main theorem. We have an invariant with following properties. Let S be a 2 knot or P2 knot. For simplicity, in this seminar, we assume whose double branched cover is integer homology S4 or integer homology minus CP2. These are not essential conditions. However, in this seminar, for simplicity, we assume this condition. Then we have non-negative integer valued invariant, this such that they have following 4 properties. Firstly, they are pairwise diffeomorphic invariant. So if two knot or P2 knots are pairwise diffeomorphic, then our invariant coincides. And for second property, we have connected sum formula. They are multiplicative. And the third property is if U is a knot of 2 knot or P2 knot. And if U is P2 unknot, we assume the normal Euler number equals to 2. Then we have our invariant equals to 1. And the fourth property, let K be a minus 237 Plato knot, and let tau small k alpha of large capital K is the 2 knot that is given by K twist alpha roll span knot. Then if K is even and the half of K plus alpha is odd, then our invariant equals to 3. So this is the second theorem. To construct this invariant, we use real Seiberg-Gitten theory. This is a variant of a Seiberg-Gitten theory. Before we explain what is real Seiberg-Gitten theory, let me explain sketch of the proof of the first main theorem. Let K is minus 237 Plato knot, and P0 is P2 unknot. Note that the double branched cover along this P2 knot is minus CP2, and the image of P0 is the real part of minus CP2. Then from the third property, our invariant of P0 equals to 1. And from connected sum formula and this property, the P2 knot given by the connected sum with 2 knot, this is n times connected sum of 1 roll span of this knot. Then our invariant equals equals to n times n power of 3. So that if n not equals to m, they are not pairwisely diffeomorphic. However, the fundamental group of the complement of these P2 nodes are isomorphic to Z over 2 for all n. Then, by using the result of Terry-Lawson or Olson-Conway-Powell, we can conclude that these P2 nodes are topologically isotopic. Then we finish the proof of theorem 1. So this is the sketch of the proof. So let me explain real cybergrid theory. This is a variant of cybergrid theory. However, this is not an Z over 2 equivariant cybergrid theory. So let us recall ordinary cybergrid theory. If X is for manifold, closed-oriented for manifold, and S be a species structure, we have cybergrid equations, and cybergrid invariant is given by signed count of the solution up to gauge transformation. So this is a picture of ordinary cybergrid equations, ordinary cybergrid theory. The real cybergrid theory, the setting of the real cybergrid theory is as follows. Let iota be an involution of a on X that satisfies topological conditions. For example, that condition is satisfied if the codimension of the fixed point part of this involution is 2. Then, and if there exists a species structure S such that the species structure is reversed by this involution, then we have an involution on this species structure such that have following properties. If we define the action of this involution on configuration space of the cybergrid equations as follows, then the cybergrid equation is equivariant under this involution. And let U be a gauge transformation, then that satisfies this relation. If we consider equivariant cybergrid theory, then the lift of the group action satisfies this relation. However, in the real cybergrid theory, capital I reverses the U action. So capital I is an antilinear involution. And capital I is a lift of this involution. So in this situation, we can consider solution of the cybergrid equations that is fixed by capital I. So if the solution on cybergrid solution of cybergrid equation that is fixed by capital I, then we call this is a solution of real cyberbit equations. So we call the pair species structure and this antilinear involution. We call this pair is real cyberbit real species structure. So the classification of real species structure is given by the classification of real line bundle on X with z/2 action. So this is the picture of real cyberbit theory. And note that the formal dimension of real cyberbit moduli space is given by this, So this is the dimension of the fixed iota pullback fixed point part of H plus. So in the ordinary cyberbit theory, there is a constant term of the formula of the formal dimension of modular space. However, there's no -1 term of the formal dimension of the real cyberbit modular space. This is a key point. So let me explain the construction of our invariant. Let S in S4 be a 2 knot or P2 knot. And for simplicity, we assume the double branched cover along S is integer homology S4 or integer homology minus CP2. Under these assumptions, there exists unique real species structure with its real formal dimension equals to 0. So our invariant is given by absolute value of the signed count of real cyberbit equations up to gauge transformations. In real cyberbit theory, gauge transformation is a subgroup of ordinary gauge transformation that is fixed by our involution. So for little bit technical reason, we consider index 2 subgroup of full gauge group. This is the definition of our invariant. And we have to take absolute value of the signed count of the real cyberbit solutions because we have no canonical orientation on real cyberbit modular space. Here is an alternative definition of our invariant. So we can construct real version of Bauer-Fulta invariant on this for manifold with involution. The involution is given by covering transformation. Then real version of Bauer-Fulta invariant lives in these colimits. And note that they are same dimension. So that if we forget, and this part is, there is a plus minus one action on this part. So if we forget plus minus one action on this part, this is just a homotopy class of the map Sn to Sn. They are same dimensions. So we can take mapping degree of this map. So this is an alternative definition of our invariant. So let me explain why does our invariant work well on this four manifold. In the case of ordinary Seiberg-Witten theory, under this condition, for all species structure, the formal dimension of the ordinary Seiberg-Witten modular space is less than -1. So we take generic metric and generic perturbations. We have no irreducible solutions. However, in the case of real Seiberg-Witten theory, there exists real species structure whose formal dimension of real Seiberg-Witten modular space equals to 0. So there can be there can be irreducible solution of real Seiberg-Witten equations. Here is an example. Let us consider the two knot. That is one load span of -237 Pletzer knot. And this is a picture of framed modular space of ordinary Seiberg-Witten equations on this four manifold. This is double branched cover along these two knots. There are two irreducible solutions and one reducible solutions. If we take a specific metric, and this is a framed modular space, so that there is U1 action on these irreducible solutions. And then we take capital I invariant part of this framed modular space. There's 5 points in real in framed modular space. So there are 4 irreducible solutions, and these two solutions are switched by -1 action. These are also switched by -1 action. And the spectral flow of these spectral flow between these reducible solutions and irreducible solution is 1, so that we can compute our invariant is 3. So this is the example of our invariant. This is the example of our situation. So let me explain the history of real Seiberg-Witten theory. Firstly, Tian 1 considered Seiberg-Witten equations with real involutions for real element manifolds. After that, Nobuhiro Nakamura considered real Seiberg-Witten theory for the case that involution is free. This is the first application of the real cybergrid theory to topology. Nakamura proved 10 over 8 type inequality with local coefficient on the quotient for manifold, and he construct a real version of cybergrid invariant. After that, Yuya Kato consider the real cybergrid theory when the involution have non-empty fixed point part, and he proved 10 over type inequality, real version of 10 over type inequality. Kato considered closed form manifold with involution, and Konno, Taniguchi, and I considered the case that the boundary is not empty, and we generalize Kato's inequality, and we prove Broglie type inequality of real version. Jakai Lee construct real version of monopole flow homology, and he proved that surgery exact triangle of the real monopole flow homology. Let me explain other applications of our invariant. Let C0 be quadratic curve in CP2. This is called conic. And you know that quadratic curve is diffeomorphic to S2. And I construct an infinite family of embedding of S2 to CP2 such that the fundamental group of whose complement is isomorphic to Z over 2, and they have same homology class. However, they are not smoothly diffeomorphic. We can prove this part using our invariant. And after I submitted my paper to the archive, Andreas Juhas pointed out that using the result of Kim and Ruberman, we can prove that these embedding of S2 are topologically isotopic. Conway-Olson gave another proof of they are topologically equivalent. And here is other application. So this is a partial solution of a problem of Kirby list. This is posted by Melvin. It is known that K twist span knot of K twist the connected sum of K twist span knot and P2 knot whose standard P2 knot, the knot group only depends the parity of K. So there is a question that if the parity of K coincides, these P2 knots smooth equivalent or not. So here is a here is a counter example of this question. Let K be a -237 Pletzer knot and k is even integer, then the connected sum is P0 and k twist span knot and k plus 2 twist span knot of k. They are not smoothly isotopic. So this is a corollary of our calculation of the invariant. So there are 30 minutes left. So I will explain how to calculate our invariant for the double branched cover along one rolling span 2 knot. So let me record twist and rolling span 2 knot of k. This is 1 knot in S3. So let me explain span 2 knot. We have the decomposition of S4 like this. And let us consider this part. So if we take knot in D3 and let me consider the tubular neighborhood of this knot, then if we remove the tubular neighborhood of this cross S1 and let us attach the tubular neighborhood of knot cross S1 to this part, we have such a four manifold. Then we can decompose S4 like this. Let me call this four manifold P. This four manifold is called Montesinos twin. So one can check that the boundary of this four manifold is diffeomorphic to T3. And we can more easily check that the boundary of this four manifold is also T3. So S4 is given by pasting two four manifolds along their boundary. So there are embedding of S2 in P. This is given by the knot cross S1, this cross S1, and the north pole and the south pole cross T2. So this is the part of the knot cross S1. This is a cylinder, and we attach two discs here. This is embedded in the Montesinos twin, and this is diffeomorphic to S2. So we call this embedded S2 is S. So we call span 2 knot. So we call the image of S in this decomposition of S4. S is span of the knot K. So it is known that if we twist the pasting diffeomorphism like this, let K and alpha be an integer, then we can this for manifold is again diffeomorphic to S4, and the image of S in this decomposition we called S is K twist and alpha roll span 2 knot. So under this construction, let me explain how to calculate our invariant. If small k is even, then the double branched cover of this 2 knot is given by the let xk be this for manifold with boundary, and the tilde of xk is double cover of this for manifold given by the double cover of meridian of this knot. And let P tilde is double branched cover along S. They are for manifolds with involution and a boundary. The boundary is again diffeomorphic to T3. And if T is even, the double branched cover along this 2 knot is given by x k tilde and p tilde pasting by this diffeomorphism. The diffeomorphism a half k comma alpha is given by this matrix. So if k is even, then there exists a unique real species structure such that this invariant is given by the product of these relative invariants. So let me remark about the relative invariant. So the boundary of these four manifold is T3, and the double cover of this boundary is given by given by this. This is also diffeomorphic to T3, and the involution is given by this in first column. Then for any real species structure on tilde T3, then the real version of Seiberg-Witten flow homotopy type equals to this one. That is, there is only one reducible solutions. There is only one reducible solution, and that is its linearization is invertible, and the eta invariant equals to 0, so that we have real version of relative Bauer-Filter invariant like this. So if we take the absolute value of these absolute value of degree of this map, we can define relative invariant of them. So let me explain real species structure and relative invariant of these four manifolds. On xk tilde, there are two real species structures. They are real species structures, and one real species structure, our invariant always equals to 1, and other is our invariant can be non-trivial. And on P tilde, for any real species structure, our invariant equals to 1. So the problem is that when is this real species structure extended to all of the four manifolds? That is, when this real species structure extended to P tilde. So let me explain the real species structure on boundary. So there are 4 real species structures on T tilde 3. So here is a little bit technical explanation, and the conclusion is there are 4 real species structure on this 4 manifold, and the conclusion is that if this pasting map satisfies these conditions, then we can extend this real species structure to this 4 manifold. Then we have non-trivial invariant of our invariant. We have non-trivial invariant. So maybe I speak a little bit too fast, and I want to finish my seminar. Thank you for the listening.
Well, thank you for the talk. It's very late there, we know. Other questions?
I have a question.
Sorry,
So,
go ahead. Yeah.
oh, all right, I'll go.
Yeah.
But go next. But if so I guess you have to get a little bit lucky, or maybe not so lucky, to make the fundamental, for your examples, to give the RP2s, you have to get the fundamental group correct. But then afterwards, you also have to have the right calculation of your invariant. So in the end, if you did this with some other knot, no, so not the pretzel knot, do you know, forgetting the fundamental group for a minute, do you know, are you basically that number 3, which you got as the answer for your invariant, is that determined by some classical knot invariant of K?
Yes. I think we can calculate our invariant for some invariant of not K. But I don't know what the invariant actually is. So
do you suspect that it's a classical invariant?
maybe I guess that this is because maybe this is related to some Euler number of real monopole from homology along double branched cover of K, and there is surgery exact triangle of real monopole from homology, and maybe we can compute scale relation of the knot K. So maybe I think this is related to some classical invariant of knot K. But for now, I don't know what actually is.
Okay, thank you. Yeah, it just
thank
seems
you very much.
It must be some invariant. So either it's a classical invariant, which would be interesting, or maybe it's a new invariant, which would also be interesting. So anyway, I think you win.
Thank you very much.
Hi, Jin. It was a great
Hi.
talk. I was wondering about the end calculation with T3, right? So you have B1 greater than 0, right? So are you using like the unfolded version
No,
of
no,
floor
no.
spectrum?
So in real cybergrid situation, so the role of B1 is in real version. This is dimension of minus iota fixed point part of first homology. And the involution iota is given by
And so it's a free action.
Yes, this is free action, and iota pullback fixes all elements of first cohomology class. So in the real situation, there are the real version of cybergrid Flair homotopy type of tilde K3, tilde T3 is the same situation in the ordinary, same situation of homology, integer homology 3 sphere in ordinary cybergrid theory. Does it make sense?
Oh, that's interesting. Okay, so like in this situation, like the Picard torus just like disappears. Okay. Yeah, I'll buy it.
Thank you very
Thank
much.
you.
That's very cool. Are there further questions?
Mhm.
So, in this theory, what is like if you want to construct Floer homology for three manifolds, what would be the invariant of the unknot? Is it just, I mean, I guess what this is going to be, I'm gonna just try to understand why, so like, you don't have a, you look at, you take two knots and you connected some them and you don't get a non-trivial, you would get a non-trivial invariant, right? So something interesting should be happening for the invariant, for the Floer homology of the unknot here, right?
For unknot, sorry,
For the one dimension, like unknot in S3.
unknot in S3, and so
I guess the first thing is that how does it work? Like, is it like formally similar to the ordinary monopole Floer homology that you have three flavors? And...
sorry. Could
Hey,
you?
Yeah, what I guess, sorry, I'm asking a bunch of great questions. But like the first thing is that what is the invariant of the unknot in S3, the Floer homological invariant of the unknot in S3?
This is
Rank 1.
This is so the H real version of monopole homology equals to this is in 0/2 coefficient. 0/2 coefficient. This is 0/2 polynomial ring. This is this is Borel homology of point. And sorry.
Right.
I don't know. I can answer your question or not.
No, I think you did. But somehow, like in the case of the unknot, you're reducible. I mean, this is coming from a reducible, right?
Yes.
But like
coming from reducible.
This is like but the group, it's the stabilizer of the reducible is Z mod 2.
Yes.
I see.
Yes. Thank you very much.
Okay, yeah, thank you. Thank you.
So I just logged on. I don't know if anyone asked this question, but I wanted to ask: why are you working with Floer homotopy in your paper instead of just Floer homology? The invariant is just homological, right?
Yes.
It's just technically. What are the technical advantages?
So there are no deep reason for now. But firstly, I a little bit consider that if we consider the spin case, then we have Z/4 action that is given by J action. Then firstly, I thought that we have more strong invariant that is that comes from Z/4 or equivalent homotopy theory. But in this paper, I cannot construct such a strong invariant. However, in this seminar, I didn't explain the example. However, in my paper, there is an example of exotic S2 in CP2 and bar and many CP2 that is distinguished by stable homotopy class of real version of Bauer-Fulton invariant. So this case, we cannot distinguish. Maybe we cannot distinguish. Just to consider Flare homologic or such invariants. Maybe.
I see. Thank you.
Thank you very much.